In a feat that defies the boundaries of human achievement, NASA's Voyager 2 spacecraft, launched in 1977, has once again rewritten the annals of space exploration with a discovery that challenges everything we thought we knew about the edge of our solar system. It's an intrepid probe, now more than 12 billion miles from Earth, has ventured beyond the heliosphere, the protective bubble of particles and magnetic fields generated by the sun, and into the uncharted waters of interstellar space. What it has found there, at the very frontier where the sun's influence fades and the galaxy begins, is nothing short of astonishing. The data streaming back from Voyager 2's aging instruments paints a picture of a cosmic boundary that is far more complex, dynamic, and mysterious than scientists ever predicted. This isn't just a new chapter in heliophysics. It's a revelation that forces us to rethink the very nature of our solar system's place in the galaxy. The discoveries made by Voyager 2 to cross the heliopause, the boundary marking the edge of the heliosphere, have appended decades of theoretical models, revealing phenomena that seemed at first glance impossible. Voyager 2's journey to this point has been nothing short of epic. Launched on August 20th, 1977, the spacecraft was designed to explore the outer planets, conducting flybys of Jupiter, Saturn, Uranus, and Neptune. After completing its primary mission, it continued its voyage, propelled by a radioisotope thermoelectric generator that converts the heat from decaying plutonium into electricity. Despite its 1970s-era technology, Voyager 2 has endured the harsh conditions of deep space for nearly half a century, traveling at speeds of over 34,000 mph. By November 5, 2018, it crossed the heliopause at a distance of 119 astronomical units, about 11 billion miles from the Sun, becoming only the second human-made object after its twin, Voyager 1, to enter interstellar space. Unlike Voyager 1, which crossed the heliopause in 2012, Voyager 2 carries a working plasma science experiment, providing unique insights into the nature of this cosmic boundary. The data it has sent back since then, particularly in recent years, has revealed a region of space that defies all expectations, as Voyager 2 breached the heliopause. Its instruments began detecting anomalies that left scientists stunned. The heliopause was expected to be a relatively simple boundary, a transition zone, where the solar wind, a stream of charged particles emanating from the sun, gives way to the interstellar medium, the sparse plasma and magnetic fields that fill the space between stars. Models predicted a gradual shift in particle density, a weakening of the sun's magnetic field, and an increase in galactic cosmic rays, high-energy particles accelerated by distant supernova or other cosmic events. But what Voyager 2 found was anything but gradual or predictable. Its cosmic ray subsystem recorded dramatic surges in cosmic ray intensity, not in a uniform distribution as anticipated, but in strange, pulsating waves that ebbed and flowed with no apparent rhythm. These weren't random fluctuations. They were patterned, suggesting some unseen structure or force was shaping their behavior. Even more perplexing was the behavior of the magnetic field. Scientists had assumed that as Voyager 2 crossed the heliopause, the sun's magnetic field would weaken and become disordered, giving way to the chaotic, magnetic environment of interstellar space. Instead, the spacecraft's magnetometer detected a field that was not only stronger than expected, nearly 3 times the intensity observed by Voyager 1 in 2012, but also highly ordered. Remarkably, the magnetic field just beyond the heliopause was aligned parallel to the field inside the heliosphere, a finding consistent with Voyager 1's observation, but still baffling. This alignment suggests that the transition from solar to interstellar space is not a chaotic handover, but a structured interface, possibly shaped by larger galactic forces. The discovery challenges the long-held assumption that the heliopause is a diffuse boundary, proposing instead that it may be a sharply defined frontier with properties we are only beginning to understand. The plasma environment Voyager 2 encountered added another layer of mystery. Inside the heliosphere, the plasma is hot and sparse, dominated by the solar wind. In interstellar space, it was expected to be colder and denser, shaped by the remnants of ancient stellar explosions. But Voyager 2 found something entirely different. Plasma that was denser than the solar wind, yet colder than typical interstellar plasma. As if caught in a strange in-between state, this unexpected zone detected just before and after the heliopause crossing suggests the presence of a transitional layera, kind of cosmic buffer zone that separates the heliosphere from the broader interstellar medium. The plasma science experiment measured a slight increase in plasma density just inside the heliopause, indicating compression, followed by a sharp drop in solar wind particles once the boundary was crossed. This wasn't just a change in density, it was a shift in the fundamental nature of the plasma, hinting at processes that don't align with either solar or interstellar dynamics, adding to the enigma. Voyager 2's radio signals began exhibiting subtle distortions as they traveled back to Earth. These signals, transmitted across billions of miles, showed frequency shifts and phase modulations that suggested the presence of complex structures in the plasma. Scientists analyzing the data found evidence of eddies or folds in the interstellar medium, akin to ripples or currents in a turbulent sea. These structures weren't random. They appeared to form coherent patterns, possibly driven by large-scale magnetic or electric fields. The idea that the heliopause could host such dynamic, organized features challenges the notion of a passive boundary. Instead, it suggests that the edge of the solar system is a region of active interaction, where solar and galactic forces collide and reshape one another in unpredictable ways. One of the most startling discoveries was the detection of magnetic reconnection events, sudden, explosive realignments of magnetic field lines that release bursts of energy. These events, typically associated with intense environments near stars or black holes, were thought to be impossible in the relatively calm expanse of interstellar space. Yet, Voyager 2's magnetometer recorded rapid shifts in magnetic polarity, accompanied by spikes in particle energy, indicating that such events were occurring far from any stellar body. These reconnections suggest that the heliopause is not a static barrier, but a dynamic region where electromagnetic forces are in constant flux. The energy released by these events could influence the behavior of particles and fields across vast distances, potentially shaping the structure of the heliosphere itself. Perhaps the most intriguing finding was the directional asymmetry in cosmic ray distribution. Voyager 2's cosmic ray detector observed that high-energy particles were arriving predominantly from one direction, rather than being evenly distributed as models predicted. These particles, originating from galactic or even extragalactic sources, appear to be focused or deflected as if guided by an unseen lens or barrier. This asymmetry suggests the presence of a large-scale structure, possibly a magnetic filament, or a gravitational feature that is altering the trajectory of cosmic rays. Some scientists speculate that this could be evidence of a magnetic wake created by the solar system's motion through the galaxy, much like the wake left by a boat moving through water. Alternatively, it might indicate the presence of galactic magnetic structures vast and stable enough to influence particle paths across light years. Such structures, if they exist, would represent a kind of cosmic scaffolding, organizing the interstellar medium in ways we've only begun to explore. The implications of these findings are profound, not just for astrophysics, but for our understanding of the solar system's role in the galactic ecosystem. For decades, the heliopause was seen as a clear demarcation, the point where the sun's influence ended and interstellar space began. Voyager 2's data suggests otherwise, portraying the heliopause as a semi-permeable membrane that interacts dynamically with the surrounding galaxy. This boundary may act as a shield, deflecting more than 70% of cosmic rays that would otherwise bombard the inner planets. But it's not a fixed shield. Its shape and properties shift in response to solar activity and galactic conditions. The sun moves through the Milky Way, encountering clouds of gas, magnetic fields, or even dark matter. The heliopause could contract or expand, potentially exposing Earth to increased radiation. Such changes might have influenced climate, biological evolution, or even mass extinctions over geological timescales.